using video as a prompt, just like large language models use text prompt to generate more text. What if you could, instead of just explaining what video you want with text and maybe an image, you could also use a different video to show how to generate your video. So let's say you have this image and you show this video of the person dancing, and you use that to make this your video dance in the same way. Very good innovation. So they have this diffusion transformer that generates the video and then make a copy of that. And this other copy is for processing the reference video, the prompt video, the person dancing. So this copy will process your reference video and it will create instructions and guide for this generator. And they will merge their attention mechanism. So they will train this guy, this transformer, to understand your reference video, and then it will instruct this generator on how to generate it. So let's dive deeper. There are two ways of controlling video generation. One is structural. For example, when you give it depth map here, it shows a structure, or human pose. Like here, you can give it this. Or segment masking. Here, and then these are cars and roads. And then you describe what you want in addition to these structural videos or materials that guide it. So you basically guide it with different video in pixels, and this is a lot better studied and understood than semantic control generation. This is when you just describe with text. I want Minecraft style, make an object expand like a balloon or perform a specific dance, and you can control motion style concept camera just by describing it with words. And in the past, this was done, for example, with LoRa's, where you train a LoRa just for the Minecraft style or just for some specific edit, which doesn't scale so well because you need to do every single one by one manually. The key idea of this paper is video as a prompt. So it reframes the problem as in-context generation. So you just give the video as a prompt, just like you give prompt to large language models. The input includes reference video, for example, a car turning into Minecraft blocks. So this is an example of what you want to do. And then reference image is the first frame of your video. For example, a picture of a dog now. And captions, which is text description of the both reference and the target video, explaining what you want the model to generate. To make this work, they have two key innovations. Plug and play mixture of transformers, so they will not fine-tune the big video diffusion transformer. They will just freeze it. This way they not only avoid spending a lot of compute, but also issues with catastrophic forgetting, where you teach the transformer to do one thing and then it overrides what it knew before. Because it's updating its weights, changing its weights to be able to do this new thing, but then those weights were something else. So you need to be careful, need to keep teaching it both of the skills at the same time. Mixture of transformers includes frozen backbone, which is the original pre-trained video generation model, and its job is to handle the video generation of the target video. Then we have trainable diffusion transformer, which is the copy of this frozen backbone. So much about saving resources. Now we are actually having a full-sized copy, but we are just training that one. We're not training the frozen one. But this way we will prevent catastrophic forgetting on this frozen diffusion transformer. And example of this frozen backbone would be Cog Video X or 1.2.1. And then identical copy with the same weights of that frozen backbone is created, and this one will be trained. There are multiple reasons to just copy it. First of all, it's gonna have same knowledge about styles, data, videos, and then the convergence of the two will be easier with less data. They will be able to work together easier. Also, we have perfect architectural alignment. It's easy to stitch them together. They're not so different. We can easily combine their two attention mechanisms of different layers into a single attention, full attention. It says here in context full attention and covering both of them. And this is a very nice way to deal with catastrophic forgetting, because now we don't care if this trained model forgets what it previously knew or some of the things, because this frozen model will know all of that. And so their roles during training are different. So the frozen backbone is just converting the noise to video. And the trainable expert is for interpreting the reference video, the video prompt, understanding the style, what it needs to, and then interpreting it, processing the style, the tokens, and then helping with this full attention. It's gonna guide this generator to use that style, and everything else it learns from the video prompt. The way this full attention works, you would need to understand the attention mechanism. Here there are a lot of YouTube videos. I made videos coding DeepSeek v3 from scratch, coding Llama 4 from scratch. So they're gonna merge their attention queries. So from backbone and from expert, just merge them into a single query or a single matrix of queries of all tokens. Also concatenate the keys and values as well. And now perform a single big attention with all of these key query values full matrices. This will allow information from this expert layer that's interpreting the prompt video to communicate that information to the generator with attention mechanism, because attention mechanism is like getting and merging and blending information. So that's how we will just transfer information on how to generate, on the style, on what to do. But importantly, it's not that we are just communicating from the prompt transformer to the generation transformer. We're also communicating back, because the prompt transformer is looking at the current generation and it's updating its guide on what to do with the generation by looking at the generation with the attention mechanism. So they are connected, each layer is connected and they're communicating with each other. Generator is following the guide and the guide transformer is updating the guide based on what generator is doing. Now the problem here is we have two transformers, and when they assign positions to their videos, the raw rotary positional embeddings, showing where each video, where each patch, where each frame is, we're actually gonna get that, for example, there is fifth frame in one video, in one transformer, and that same position in the second transformer. So we will have duplicated positions. And if we do attention mechanism with those copy duplicated positions, it will not know which frame belongs to which transformer. So it will not know which frame is the guide, which frame is the currently being generated one. And this is what could happen. So if we have this reference video, it's a dog statue or something being turned into gold, and reference image frog. So now it means we want a video of a frog statue being turned to gold. But if we don't do positional encoders properly, it will not know which video. You see that now it's mixing the textures of the frog, so it makes the dog and this whole video a bit green, but it also keeps the dog. So it doesn't know which one is the reference and which one it needs to generate. And so the way we're gonna change these positional embeddings is we're not gonna change spatial embedding. So if we have image, it's gonna be divided into patches, little parts of the image and frames. We're not gonna change that, but we will change temporal embeddings. We will make the reference video appear as if it happened before the generated video or the image. So we will shift the time for the reference video, and they're gonna shift it into negative, so that it starts from -1000, -900 seconds, or this would be the frame, or the way, whatever the way of encoding positions. And then target video frames will go from 0, 1, 2, 3. And now it knows what the reference video is and what the target generating frames and patches and tokens are when it's in the attention mechanism. And one more thing, this transformer is not necessarily looking at the second frame and applying whatever it learned at second frame to the second frame in generation, because maybe in the first few frames, there is nothing, there is no subject in this generated video, or there is no subject in the or reference video. So it's actually gonna look generally at the reference video and take out general patterns and apply to the subject video frames, regardless of, it's not gonna just map frame to frame. And so that's why these positional embeddings help. When we make it understand which video, we just separate, make this video as if it happened before the reference video. That's gonna be it for this video. Join my school to become AI researcher. We have all of these courses, link below the video.